So for AI to continue advancing, we basically need two things, right? We need more computational power for sure, and also we need to make the data movement becomes faster and also more energy efficient. So in engineering terms, we talk about things like higher communication bandwidth and also better energy efficiency. Okay? And solving this kind of data communication bottleneck, it's just becoming as important as making our microprocessors becomes faster and more powerful.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potka. From artificial intelligence to quantum computing, cybersecurity, and next-generation communications, computers and advanced electronic components are essential to ensure and extend American leadership in key critical and emerging technologies. We're joined today by Qing Cao, a professor supported in part by NSF, whose lab is developing new materials and techniques for electronic and optoelectronic devices, including a monolithic 3D silicon integrated microchip that may help surpass data bottlenecks and current AI workloads. Professor Cao, thank you so much for joining us today.
Oh, thank you. Thank you for the opportunity.
So I want to start with kind of the big thing that we're talking about today. What is a monolithic 3D integrated silicon microchip?
So most of us kind of like pretty familiar with what silicon chip is, right? They're the foundation of modern microelectronics. It's kind of like powering everything we have from our smartphones to laptops to current kind of very powerful AI systems. Traditionally, if you think about microprocessor chips, they're built like single-story city, right? We have all the components that are kind of arranged side by side on a flat surface. So a monolithic 3D integrated chip take a little bit different approach. So instead of spreading everything out, right, we actually stack layers of components, which we call transistors, vertically. We're almost like building a skyscraper instead of expanding a city horizontally only. And the word monolithic here means that all of these layers, they're actually built and integrated on the same underlying starting silicon substrate in a layer-by-layer fashion. And here, by stacking devices in the vertical dimension, right, we can pack more functionalities into the same chip area footprint while improving the performance and energy efficiency at the same time.
And I think this has been a real goal of computing microchip manufacturing industry as things get smaller and smaller now to make it denser. Right.
Yeah, exactly. Right. We always, we talk about Moore's law, right? So we always try to get higher integration density, better functionality, better performance, and better energy efficiency at the same time. So this is a kind of another way for us to do it nowadays.
You mentioned artificial intelligence models, and that's going to be probably a big hit here. How is AI impacting current microchips?
Well, I mean, AI is definitely the biggest kind of like driving force in semiconductor industry nowadays. So modern AI systems, on one hand, as you probably hear from all the news reports around us, we need enormous amount of computational power and memory. And that's basically the reason why all those companies like NVIDIA, Intel, AMD, Samsung, and Micron just become so prominent during the past few years. And at the same time, AI also depends on big data. So for all these AI working loads, we have to move huge amount of data throughout our computational system and even within each individual computer chips. So for many of these AI workloads, the challenge isn't just to perform the computations themselves, it's actually getting the right data to the right place quickly enough. Right. So for AI to continue advancing, we basically need two things, right? We need more computational power for sure, and also we need to make the data movement becomes faster and also more energy efficient. So in engineering terms, we talk about things like higher communication bandwidth and also better energy efficiency. Okay? And solving this kind of data communication bottleneck, it's just becoming as important as making our microprocessors becomes faster and more powerful.
So how might the 3D structures, the vertical scaling of the chips, solve some of these problems?
So the vertical scaling here help us to address these two challenges facing the semiconductor industry for the demand of AI at the same time. So the first is continuing the performance improvement. Right? So let's look at this problem from a little bit of historical perspective. For decades, right, the semiconductor industry followed what we called the Moore's law, right? And Moore's law basically saying, okay, we're going to make the transistors, the basic building blocks we described previously, become smaller and smaller. Shrinking this individual component smaller and smaller allow us to pack more and more devices within the same chip area. Therefore, that's increase our computational power. That's pretty straightforward. But the problem is we are approaching the fundamental physics limit. Right. Nowadays, if you look at the state-of-the-art transistors used in our most advanced microprocessors, we're talking about a 2 nanometer, 3 nanometer technology node. The critical dimension of those devices is actually down to tens of nanometers. And in this length scale, the quantum effects, especially the direct tunneling, becomes important, and they start to degrade our transistor operations. Right. And that makes the further lateral scaling just along the X and Y directions just becoming increasingly difficult and also economically more and more expensive. So that's where this vertical scaling, right, along the Z direction comes in. So instead of just making our transistors become smaller, we can stack them one on top of another, right? And that's also going to help us to increase the integration density, or so-called the number of transistors in the same chip area, so we still get better performance and more computational power for the AI workload. And the second challenge over here is basically the data communication I described previously. Right? So as you can imagine, when you stack the devices in the vertical direction, then the device in the top layer and the device in the bottom layer, they can be connected through much shorter vertical pathways rather than going through relatively long kind of lateral connection pathways. And the shorter electrical connections between those devices and the circuit blocks means the data over here, right, can transfer faster while consuming less amount of energy. And that is especially important for AI systems.
Right. We hear about the data centers and all the cooling needs and things that are going on with the AI technologies.
Right. The energy efficiency is critical. And if you think about the overall energy consumption of the AI system, probably it depending on your application, but up to 40, even up to 90% of the delay and energy consumption is actually caused by the data communication rather than the computation itself.
So can we talk a little bit about your manufacturing technique? You have an interesting way you're going about getting these together.
Well, okay, so we think building chips in the 3D fashion makes sense, right? I mean, everything in the real physical world, they're kind of 3-dimensional rather than 2-dimensional. Our brain is 3-dimensional. So the biggest challenge in building this 3D integrated chip is something we call as thermal budget. When you try to build a new layer of transistors on top of your existing CPU or GPU chips, you typically need very high temperature. And when we say high temperature, we talk about close to 1,000 degrees Celsius, right? To first create high quality semiconductor materials. And then we need to convert this high quality semiconductor materials into high performance transistors or other type of semiconductor devices. Both here typically need about 1,000 degrees Celsius as their processing temperature. And unfortunately, here, this high temperature can damage or even destroy the bottom layer that has already been built using the conventional process. And that's the reason why, stacking those transistors in the vertical direction sounds pretty straightforward in principle, and the benefits are pretty obvious. But the real challenge here is how are we going to be able to do that so we can keep the temperature below just about 400 degrees Celsius when we build the top layers without sacrificing their performance. So the 400 degrees Celsius is basically our thermal budget over here. So one solution we provided in this research is, okay, how about we separate the material preparation from basically the vertical stacking process. So here we first kind of create an ultra-thin single crystalline silicon nanomembrane from a commercial donor wafer. And then we gently transfer this film using a process kind of like very similar to roll laminator you're going to use back at your house. And this transfer process can be completed at a temperature below 200 degrees Celsius. And after transfer, so now we have this high quality single crystal silicon film, and then we fabricate a specialized transistor called a junctionless transistor, which are designed to achieve high performance while remaining compatible with the low temperature process, which is going to stay below the 400 degrees Celsius thermal budget. And here we repeat this process so we can build devices on different layers, and then we connect these devices using vertical interconnect vias so we can have functional monolithic 3D integrated logic circuits.
Kind of to summarize, in traditional manufacturing, if you're trying to go 3D, you might melt or otherwise damage the lower layers as you're building up. And your solution is to essentially make thinner sheets and then put them together afterwards. And that way you're not damaging anything underneath, and you're kind of just being more efficient about how you're going about getting there.
You're definitely correct, right? So the major challenge over here is to control the temperature. Again, as a summary, we did two things to do it, right? One is we don't try to grow this material directly. We actually transfer this material from another donor wafer, and we transfer a kind of very thin silicon membrane, and it has many benefits, right, compared to the conventional process. And then the second is after transfer, right, we convert them into a novel type of device architecture called junctionless transistors, right? So we still get comparable performance with conventional silicon transistors, but the overall, manufacturing temperature can be kept below 400 degrees Celsius.
Very cool. So moving on from here, you talked a little bit here about how difficult it is putting it together. So I want to think about getting it out into the world and being used in existing silicon foundries. Is this a technology that can translate very easily? And what are kind of your next steps to making that happen?
That's exactly what we are aiming at for the next step. So first of all, we're definitely encouraged by the progress we have already made so far. So basically, in here we have demonstrated that our technology can be scaled to 200 millimeter wafers. We achieved pretty good device performance comparable to the high performance, conventional silicon transistors we call MOSFET. And also we have a very good device yield, on average about 98%, which is very impressive considering the entire thing is carried out in academic research lab rather than the semiconductor foundries we have in those companies. And also we have built successfully in 3D integrated circuits, including both logic circuits and also memory circuits. And you are 100% correct, right? One very important advantage here is that our approach uses single crystalline silicon. And single crystal silicon is already the foundation of the entire semiconductor industry. In comparison, if you look at many alternative approaches from monolithic 3D integration, they kind of rely on new materials such as metal oxide semiconductors, single wall carbon nanotubes, or metal cauchogenide 2D semiconductors, which can face additional manufacturing challenge. Because our approach, right, remain compatible with silicon-based manufacturing, we believe it offers a much more direct pathway toward industry adoption. And specifically, we have already received interest from many different organizations, including Samsung, IBM, TSMC, MIT Lincoln Lab, and also venture capital investors. We're very excited to continue working with our industry partners, and hopefully we can move our technology toward commercialization in a relatively short time frame.
So I also want to ask you about your NSF support and grants you've received. How has that support impacted your career so far?
NSF has always been one of the most important supporter of my research programs at the University of Illinois. And this particular projects, right, leading to this monolithic 3D integration of silicon transistors has been supported through NSF's Future of Semiconductors program, as well as the EPMD, which stands for, I believe, Electronics, Photonics, and Magnetic Devices program within the Division of Electrical Communication and Cyber Systems. But I would like to emphasize here, right, beyond funding, NSF provides actually a very good ecosystem to help researchers move from innovations from the lab toward real-world impacts. This might be a little bit different from the traditional perspective about the image of NSF, but that's real, right, in current words. For example, we're working with all the industry partners I mentioned previously, actually through the Center for Advanced Semiconductor Chips with Accelerated Performance, which we call the ASAP Center over here. This is NSF IUCRC, which stands for Industry University Cooperative Research Center. And at the same time, we're also exploring additional opportunities through, for example, the NSF kind of translation to practice programs in parallel.
I want to ask you a follow-up there. In thinking about that, interacting with more business end of things, can you talk a little bit about the workforce development and your students? How are the students getting an opportunity to look at what might be ahead for them by running through this program?
This is very, very important, right? So NSF is not just about developing cool technologies, it's also about to develop the workforce required for, U.S. economy at large. And this is especially important for the semiconductor industry, right? If you look at the report from the CHIPS Act, right, overall, if we want to bring the chip manufacturing design back to the United States, one very big challenge is how we're going to be able to get a proper number of, from technicians to, staff scientists to researchers, like actually been working in this field. So we're trying to help on this problem from two perspectives, right? So one is this specific project, right? It's got heavily involved with microfabrication, especially the microfabrication of conventional semiconductor silicon devices. So all the undergraduate students and graduate students directly get involved in this project. They get kind of hands-on experience about working inside a clean room environment, about making those microprocessor chips, and they can fed directly, right, into the US-based semiconductor manufacturing industry in the future. And on top of that, I would like to emphasize, as part of this Future of Semiconductors program, we actually work with a local community college called Parkland College. So we built a semiconductor manufacturing technician training camp during the summer. And during this training camp, we provide this hands-on semiconductor manufacturing experience, not just to our undergraduate students, right, but also to the students in this community college. So they got the opportunities to put on the bunny suits and get into the clean room, fabricate their devices. And that's one additional effort, right, for us to, on one hand, sustain the workforce pipeline of students to fill all the technician jobs in the semiconductor fabs. And at the same time, we hope many of those community college students, after they got the experience of semiconductor manufacturing, they could get interested in that, and then maybe 50% of them going to convert to our own undergraduate students and pursue degrees in related areas such as electrical engineering, computer engineering, or material science and engineering. And this is really the result of a multi-year kind of like multi-research group, multidisciplinary collaboration. And I would say this is only becomes possible, right, under the supporting framework of NSF.
Great. So for my last question today, I want to ask you about the future. You mentioned you're working on the pathway to getting this out into the world, but I also want to ask you about other things you're excited to work on over the next couple of years.
So my group has always been working on microelectronics, and strategically, we're trying to solve the problems at different levels. I would say this particular project is relatively a near-term target because we think it's kind of like closest to commercial adoption. Converting from planar 2D transistors to kind of like 3D devices, this definitely going to be the direction to go. And I believe this is agreement from both academia and industry at the same time. Other kind of exciting things we're doing, and they're also supported by NSF. well, how about we have better integration of memory with computation, right? As I mentioned previously, the data communication is a significant bottleneck for AI-related workload. So in another project, what we're trying to do is to develop new type of memory devices that can be directly integrated on top of a silicon backbone, so we can basically let those memory devices to not only store the information, but also process the information at the same time. So that's going to dramatically reduce the data movement overhead we have in implementing AI workloads. So that's very exciting. And another area we're looking at actually is bioelectronics, right? So currently we're talking about artificial intelligence, which is great, but it's still artificial, right? We're talking about artificial neural networks, kind of building on silicon transistors, microprocessors. Another kind of very exciting project we're currently performing and with NSF support under the Growing Convergence program is to say whether we can utilize biological neural networks. And here we're talking about real kind of neurons, axons, and synapses to perform this information processing. And I would say the last aspect of major research direction in my research group is to look at kind of biomedical applications, right? So the monolithic integration has great potential not only to make high-performance computer chips or AI accelerators, it could also be important backbone technology for making better kind of image sensors or string mapping devices, biomedical implants, and solve many kind of health-related problems.
Special thanks to Qing Cao. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend, and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.